Hi everyone, welcome back to the channel. This is the 9th video in this dynamic programming series. In this video, we are going to be looking at this problem, bookshop from the CSES problem set. Now this problem is nothing but the very famous knapsack problem in dynamic programming. Now in case this is the very first video that you're watching from this playlist, I would highly recommend you to start this playlist from the first video and then follow a sequence. Okay, so let's try to see what type of a problem are we looking at in this video. Okay, so let's suppose I give you the structure, right? There are n items, let's suppose. Okay, and you have a bag here. You are the person here, you have a bag with a capacity W. Okay, this bigger W. There is a capacity of your total bag and there are n items from which you can choose certain items. Okay, you want to choose those items such that the overall weight of the items comes out to be less than equal to W and your overall value is maximized. Okay, so let's suppose I told you that W is equal to 11. W is the total capacity. So let's take an example here. Let's suppose you choose this item and this item. What is the total value that you're getting? You're getting 49 and the weight here is 11, total weight, which is less than equal to 11, correct? There is another choice that you could have made. Let's suppose this item and this item. In this case, you're getting a better value while the overall weight still remains less than equal to 11, correct? There is one more example that you could consider. Let's suppose this one and this one. Here also the total weight is less than equal to 11, but the value that you're getting from here is 55, correct? So this is kind of the best choice that you could make here for these particular n items. Fine. Now this is the main problem. We want to solve this. Obviously the very first idea that you could think of is a greedy solution, right? You might think that, okay, if we have a capacity of 11, why not we choose that item which has the maximum value while its weight is less than equal to 11. So let's suppose you choose this item. You got a value of 40 and you use the weight of 10. Now what is the weight remaining? The weight remaining is 11 minus what you have already picked up, which is 10. So the weight remaining is 1. Now you could say that, okay, again make a greedy choice. Pick up that item which has the maximum value while its weight remains less than equal to 1. So you could say, okay, that this is that particular item that you could pick up. The value that you get from this greedy choice is 50. But now if you consider the example that we had taken earlier, right? The choice that we had made earlier, it had a better value than this 50, right? We could have gone for this, this and this, right? If you look at this, choice here, it is not any greedy choice, but it still turns out to be the best choice. So what we know for a fact is that a greedy solution will not work here. We might have to try out all the possibilities. All right. So right now, what do we know? We know for a fact that a greedy solution will not work here, right? We've already seen an example. Secondly, we know that for every single element, we have a choice, whether we want to put it in our bag or not, right? So what can I say? I have 2 to the power n possibilities. If there are n items, I have 2 to the power n possibilities of constructing, like putting elements into my bag, correct? Now, what do we want to do here? We don't want to try out all these 2 to the power n possibilities. We want to come up with a certain optimization, right? So one thing that you could remember, like again, not asking you to memorize it, whenever you're given a problem and you see arrays in that problem and you think about a dynamic programming idea, okay, just try to break the problem into a prefix and a suffix. When you do something like this, what happens is that you stop caring about the entire array. You start caring about either a prefix of the array or a suffix of the array. When you do something like this, see what happens. We said that we have a capacity of 11. Okay, we want to choose the items so that the overall weight of the items remains less than equal to 11 and our value is maximized, correct? So instead of thinking about this entire array, try to think about, let's suppose, this one particular prefix. What would this mean? This would mean that I am not concerned about the entire array. I am just concerned about finding out the best answer, right? Best value that I can get for a weight of 11 in this one particular prefix. Okay, if you do something like this, see what happens. Look at the last item. We already know that for every single item, there are 2 things that we can do. Either we can pick it up or not pick it up. Let's suppose you decide to pick it up. Okay. If you pick up this last item from this prefix, what would be the array that would remain? The array that would remain is this, right? This is the array that would remain. And what would be the weight that would remain? See, initially you had a capacity of 11, right? Now, if you've decided to pick this last item from the prefix, what is the weight that you are left with? You are left with 11 minus 2, correct? So here the weight that is left is 9, correct? In case you would have decided to skip it, what would happen when you skip this item, right? You would have the same array that would remain, the same sub array that would remain, but what would be your weight? that would remain. Now the weight that would remain is still 11, right? Because you decided to skip this item. So your overall weight that is remaining would not change, correct? Initially, we were concerned about this prefix of length 3. Now, if you were to look at these smaller subproblems, we are concerned about a prefix of length 2 in both of these cases. But what is different about these two prefixes? The only thing that is different is that the capacity is different now. The capacity that is allowed is different in both of these cases. So if I've picked up my item, what is the value that I will get? I will get the value present at that item. So here in our case, it is 15. Okay. So we are getting a plus 15 in our total value. And here we're getting a plus 0 because we are not including that item. Okay. And if let's suppose this was problem 1, right? Problem 1 was what? Find out the maximum value that you could get from this prefix such that you have a capacity of W which is equal to 11. This problem broke down into two smaller subproblems. Let's call them P2 and P3, right? So let's suppose you knew the answer for P2. What is the maximum value that you could get for this particular prefix such that you have a capacity of 9? Okay, let's call it X. Fine. And let's suppose you also knew the answer for P3. What is the maximum value that you can get from a prefix of length 2 such that you have a capacity of 11? Let's call it Y. Now think about it. What is going to be the answer for P1? One of the possibilities is that you have 15 plus X. Why 15 plus X? Because you have chosen your current item, you added the value 15, and then you said what is the maximum value for this P2, which is X. So one of the possibilities is 15 plus X. The other possibility is Y. Correct? Because in the other possibility, you are not adding your current item. So it will be Y plus 0 essentially. What we've learned is that a greedy solution does not work here, right? Secondly, we are concerned about picking and not picking. Got it? Which gives us the idea that, okay, there are 2 to the power n different subsets or 2 to the power n different possibilities. And clearly, even if n is equal to 100, then this number would be just huge. We will not be able to solve it. Correct? And secondly, we also looked at this idea of breaking the problem into a prefix. Rather than thinking about the entire big problem, we thought about a prefix. Correct? When we thought about the prefix, we were also able to break it down into two smaller subproblems, which were smaller prefixes. Alright, so now let's say we are concerned about this prefix of length 3 and the capacity of 11. We also saw that if we want to solve this problem, finding out the best value for a prefix of length 3 and a capacity of 11, we broke it down into two smaller subproblems. One of them was that, okay, we chose this item, and the second one was in which we skipped this item. Correct? So we have two possibilities. One is to pick this item. When you pick this item, what is the value that you will get? First of all, you will get value of 3, right? The value of the third item, right? Now we are considering 1-based indexing here. When we are coding it, we can consider 0-based indexing as well. Okay. So when we are picking it up, we are getting value 3, right? But then what is the smaller subproblem that we are solving? Now we are solving a smaller subproblem where we are saying prefix length is equal to 2 and the capacity is what? The capacity is 11 minus the weight of your current item. Let's call it weight of 3. Yes, this is the problem that we are concerned about. What is the case where we skip it? When we skip the current item, we are not adding anything to our value, right? So we are just concerned about a prefix of smaller length, but having the same capacity. Okay, so here we are concerned about same thing. Prefix length is equal to 2 and capacity is equal to same 11. Yes, so can I say that for a given particular prefix, I am concerned about the capacity first of all, right? I want to solve this problem, that given a prefix and given a capacity, get me the maximum value that I can get from this prefix with a particular capacity. There are two things that you can do, pick it up or skip it. You are considering the maximum of these two possibilities to get your answer, right? So can I define my DP state like this? That DP of, let's suppose I comma W is equal to maximum value that we can get for the prefix of length I such that the allowed capacity is W, right? Okay. So now think about it. If you are concerned about this prefix, okay, you're concerned about this prefix of length I, you have a capacity of W. What are the two things that you can do? You can either pick up this last item or you could skip this last item. See, now we are talking about the transition, okay? How do you actually get the value of dp of I comma w? So we have two things that we can do. Either we can skip the current value. If we skip, what happens? One is skip and one is pick. Okay. If we skip the current element, what happens? We are just concerned about a prefix of smaller size but with the same capacity. So we'll say it is equal to dp of I minus 1 comma w. Prefix of smaller size but the capacity remains the same. So we are going to say that, okay, add value of I to your current answer, and then also consider the prefix of smaller size, which is going to be dp of I minus 1. What is going to be your new capacity? Your new capacity is going to be w minus weight of I. Yes. Now what would you do? If you had to find out dp of I comma w, you would just take the maximum of these two possibilities. Just take the maximum and you would get your answer for dp of I comma w. Correct? What is going to be the base case now? How do we define the base case? The smallest subproblem that we don't want to solve, for which we might already know the answer or for which we don't have to further divide it. What is that smallest subproblem? Clearly, I can say that if the prefix size itself is 0, if let's suppose this entire prefix ends here, okay, if the entire prefix is gone, then can I say I will not be able to pick up any more items? So can I say dp of 0 comma anything, 0 comma any weight is equal to 0? Because for a prefix of size 0, when you have 0 items, it doesn't matter how much weight you have. You cannot pick up any item. So the base case is this. Got it? And what is going to be your final subproblem? How do we define the final subproblem? Firstly, we look at our state. What is the meaning of our state? Then we look at what is being asked in the problem statement. In our case, the problem statement clearly says that you have n items. You have a capacity of w. Give me the best, answer. So can I say my final subproblem will be nothing but dp of n comma x? It simply means the maximum value that you can get from n items such that you have an allowed capacity of x. This is exactly what is asked in the problem statement, right? What is going to be the time complexity here? Let's try to understand that. For time complexity, what is the formula that I've told you? Number of states multiplied by average transition time. Right? This is what you learned so far. What are the number of states? See, you have dp of I comma w. I can go from 0 to n and w can go from 0 to x, right? So I can say that the number of states are order of n times x. What is the average transition time? Clearly, you are just considering the maximum of two possibilities. If you're only considering the maximum of two possibilities, then you are not essentially doing any work here. It is just an order of one type of work that you're doing. So I can say average transition time is order of 1. So final time complexity becomes what? Final time complexity becomes order of n into x. Got it? So yes, that is the solution for this knapsack problem. So this is the code for the knapsack problem that we have just discussed. Okay. So we have been given first of all two inputs, integer n and x. N is the number of items, x is the total capacity. Fine. Then we are given these two things. First is the value of every single item. Second is the weight of every single item. All right. So this is where I've taken the input. Next, what I'm doing is I'm defining my dp state. What was our dp state? We clearly said that dp of I comma j is equal to maximum value that can be attained from first I elements. Let me write it first I elements, such that the total weight allowed or the capacity allowed is j. Got it? Next, we said that, okay, the base case is very simple. If you have 0 items remaining, it doesn't matter what is the capacity. Your overall answer or your overall value will still remain 0. Got it? So we are simply saying dp of 0 comma k is equal to 0 for every k, because we cannot add any more value if 0 elements are left. Got it? So for this, what we're doing is that we are not defining the base case explicitly. We have already filled the entire dp array with zeros. Got it? Next, what did we say? We said that, okay, dp of I comma w is dependent on two things. Firstly, dp of I minus 1 comma w. Secondly, dp of I minus 1 comma w minus some value. This is what we know. So let's look at the for loops here, right? First is this first dimension, which is I, right? Which is going from 1 to n. Why 1 to n? Why not 0 to n? Because for dp of 0 comma k, we already know the values. It is 0. That is the base case. Okay. So in the second loop, we're trying to find out dp of I comma j. What is dp of I comma j? The maximum value that you can get from the first I items such that the capacity allowed is j. Got it? So this is what we're trying to find out. Now, what we're doing here is that we're calculating these two values. W is the weight of the current item. Value is the value of the current item that you can get. Now, like I said, you have two choices for the ith item. Either you can pick it up or skip it. So if you pick it up, what is the overall value that you would get? First of all, you would add this value, right? The value of the current item. And next you would say dp of I minus 1, comma, j minus this w. What is this w? This is the weight of the current item. And j is the capacity allowed for this particular prefix. Okay. So I can say for picking, obviously you're only going to pick it up when the capacity is greater than equal to your current item's weight. So this is what we're checking here. Got it? So this is the case where we pick up the current item. And the case where we skip it is very easy. We just reduce the prefix size and then we have the capacity as the same thing, right? Then we just simply say that dp of I comma j is the maximum of these two possibilities. Okay. So the final time complexity of the solution is order of n into x. The space complexity is also order of n into x. So what we just saw here is that dp of I comma j is dependent on two things. Firstly, it is dependent on dp of I minus 1 comma j, right? Secondly, it is dependent on dp of I minus 1 comma j minus some value, right? This is what we saw. Now, if you were to represent this entire, dp grid in the form of a table, how would this look like? You would simply say that, okay, this is the table. In order to find out the values of this particular row, like, this is I here basically, and this is this j. Okay. What you're saying is that in order to calculate the values of this particular row, it only depends on the values of the previous row. See, it depends on dp of I minus 1 j and I minus 1 j minus some value. So what I know for a fact is that this particular element, this green element, is first of all dependent on this value. And secondly, it is dependent on some dp of I minus 1 j minus some value, right? It is dependent on some two values in the previous row. So can I do space optimization here? Yes. Now, in case this is the very first time you're hearing about space optimization, don't worry, we've already covered space optimization in a lecture. So I would highly recommend you to check that out first and then proceed with this video. So how can we do space optimization here? We can simply say that don't maintain this entire n cross x grid in the memory, just maintain one row in your memory at a time. And that would be how much memory? That would be just order of x memory, right? So this is the space optimized code here. For calculating dp of I comma j, we are only concerned about the values in the previous row. So in order to get the answers for your current row, you would only look at the answers in your previous row, correct? So in memory, at any given point of time, I will just maintain the previous row in order to calculate my current row. Then once my current row is calculated, I will update my previous row to my current row. Got it? So first what I'm doing is I'm defining my vector previous. This is going to store the answers for the previous row. Got it? Now before you start running these for loops, this previous row is going to contain the base case dp of 0 comma k. dp of 0 comma k is going to be 0 for every single value of k. So right now the previous row contains 0 at every single place. How will you find your answer for your current row? Firstly, you must understand that dp of I comma j simply means current of j here. Okay, and dp of I minus 1 comma some j is simply equals to previous of j. Okay, this is something which is very important. Current row's jth element defines dp of I comma j. Previous row's jth element defines dp of I minus 1 comma j. Okay, so in order to get dp of I comma j, it depends on dp of I minus 1 comma j firstly. So this is the case where you skip it. This is the case where you're saying dp of I minus 1 comma j. Okay, so you're saying previous values jth index. Second was the case where you said that add the current element to your set. So you said that, okay, add the value, but then the remaining capacity would be j minus w. W is the weight of your current item, j is the current capacity. So you are concerned about dp of I minus 1 comma j minus w. Let me write it here. You are concerned about dp of I minus 1 j minus w. Okay, so this is what you're writing, previous j minus w. Like I said, dp of I minus j is simply represented by previous of j. So dp of I minus 1 j minus w will be represented by previous of j minus w. And here you just populate dp of I comma j. dp of I comma j is nothing but current row's jth index. So you say current of j is equal to the maximum of these two possibilities. Either you skip the current element, or you pick the current element. Okay. And finally you said that, okay, update your previous row's answers to your current row's answer, because when you go to the next iteration, your current row must act as the previous row. Got it? And finally, at the end, we know that the previous row would be nothing but the nth row, the last row. right? And the answer that you wanted to find out was dp of n comma x. So that would be present at previous of x. Okay, so these are both the solutions that I've told you. One was the case where you had time complexity as order of n into x and space complexity as order of n into x. This was the solution. Secondly, we looked at this solution which is optimized in terms of space, where the time complexity is still order of n into x, but the space complexity is order of x. Let's first of all look at the CSES problem that we had to solve in this video. Okay, and this problem was bookshop. Now this problem is exactly what we have just done. Okay, see, you are in a bookshop which sells n different books. You know the price and the number of pages of each book. Okay, then it is given that you have decided that the total price of your purchase has to be at most x, right? Exactly what we were discussing up until now. What is the maximum number of pages that you can buy? So if you were to look at the constraints here, n is going up till 1000. Okay, x is going up till 10 to the power 5. So the solution that we just discussed, we clearly saw that it had a time complexity of order of n into x, right? So I think now you can solve this problem on your own. Like we've just discussed the exact same problem, and the same code that we have just written will work here as well. Okay, all right, so that was it for this video, guys. I hope you were able to understand this problem. In case you understood everything that was taught in this video, don't forget to comment understood on this video, and I would see you in the next one.